Hello, this is Professor Keene. Today we're going to continue our discussion of Chapter 2 in A Student's Guide to the Great Physics texts. We're looking at the work of William Gilbert, his book on magnetism. In our previous lecture, we talked about Gilbert's discussion of how when a blacksmith heats up a piece of iron above some temperature, it loses its magnetism, but then as it cools down, sitting nearby the Earth, it acquires a magnetic behavior similar to that of the Earth. And he explains this in terms of kind of an astrological explanation. He says that just as a baby, when it is born, is affected by the location, position, orientation of the Earth compared to the stars, so too a piece of iron, as it cools, acquires the magnetic environment from the Earth on which it is found. What I'd like to do now is provide a bit more of a contemporary understanding how we think about the acquisition of magnetism today. And so what I'm going to do is I'm going to get out my sketchbook and talk a bit about paramagnetism, ferromagnetism, and the Curie point. Okay, so what I'd like to do first of all is introduce the idea. This is, again, this kind of thinking is not something that this is not the way that Gilbert thought about it. It's a much more contemporary way of thinking about it in terms of atoms and the behavior of individual atoms as magnets. So you might think in the contemporary view, so contemporary, modern, I would say, view of magnetism. And again, I'm not saying all of this is correct, I'm just saying it's a contemporary or modern view of magnetism. According to this modern view of magnetism, certain materials, like iron, are comprised of atoms that themselves act like tiny magnets. So I'm going to imagine that we have a block of material like iron, and each of the atoms itself acts like a tiny magnet. So I'm going to draw them as a whole bunch of little arrows in random directions, where one tip of the arrow, so if I draw an arrow like this, that means it's like an atom with a north end and a south end. Again, this is highly schematic, and you should not take this literally, because you'll run into problems if you do so. But the idea is that certain materials, like iron, is what's called paramagnetic above a certain temperature. What we mean by paramagnetic is each of the atoms behaves like a little magnet, but because there's high temperature, the temperature kind of scrambles up the orientation of these. So they're pointing in all different directions. So whereas each one of these individually acts like a little magnet, overall this piece of iron doesn't have an overall magnetization because it's confused. There are little magnets pointing in every different direction. This is so at high temperature, the atomic constituents have a random orientation. And that implies that the iron block is overall non-magnetic. Okay? But if you were to apply a magnetic field to this, so if you were to take this block and you were to put it in the vicinity of an applied magnetic field or a magnetic thing, like let's say you're sitting on the Earth where it's near a magnetic field that's pointing in this direction. This is a magnetic field. I'm going to give it the label B. So that's a magnetic field. It could be the magnetic field of the Earth or and some other nearby magnet. This, of course, raises the question of how that got magnetized, but let's suppose we have a nearby magnet. What's going to happen with this paramagnet is that all these little magnetic atoms are going to orient in the same direction as the ambient magnetic field is pointing. So, at high temperature, once again, at high temperature, the magnetic atoms align with an ambient that is the surrounding magnetic field. Okay, so this is the hallmark of a paramagnetic substance. Above, at high temperature, what happens is that all of these spins or all these magnetic atoms are oriented in random directions, but they will line up with an ambient magnetic field. By the way, why do these little atoms behave like little magnets? After all, in some materials don't behave this way, other materials do. It has to do with the fact that these atoms have unpaired electrons. And the unpaired electrons have magnetic moments, or they act like little magnets, and so overall these atoms act like magnets. Now, what about iron as you go to low temperature? So at low temperature, what happens is these atoms that were formerly in random directions, they end up interacting with one another so as to align with one another. So at low temperature, the magnetic atoms, so to speak, bind together in such a way that the magnetic moments or the magnetic atoms are oriented in the same way. So they're oriented parallel to one another. Okay, so we can draw what's called a phase diagram. I know you're used to solid, liquid, gas phase diagrams, but let's draw temperature versus applied magnetic field. Applied magnetic field. And I'm going to draw a phase boundary right here. And I'll label a few things and then I'll talk about them. This is the Curie temperature right there. It's a specific temperature. And at high temperature, so this is the phase diagram, the magnetic phase diagram of iron. Okay. And what happens in this region at high temperature, it behaves as a paramagnet, which means that, I'll draw a little schematic here, all these atoms are randomly oriented unless you apply a magnetic field. Oops, let me do this. If there's no magnetic field, so the applied magnetic field is 0, they're going to be oriented in random directions. But if there is a magnetic field, then they will be oriented along with that applied magnetic field. What about in this region? So this is the paramagnetic phase. The paramagnetic phase. This inside of here is called the ferromagnetic phase. And in here, even in the absence of an applied magnetic field, they will tend to orient with one another. So you have a block of material. These little magnetic atoms will co-orient, that is, they'll be parallel to one another. That happens below this temperature. So at 0 applied magnetic field, as you lower the temperature, whereas they're randomly oriented here, as you move in this direction, once you get below this critical temperature called the Curie temperature, all of those magnetic atoms will co-align and they will be in the same direction, and this will become in the ferromagnetic phase, and it will the magnetism will be locked in, so to speak. Okay, so in the ferromagnetic phase, the atoms are aligned with one another. Okay, so this is the way to think about it. Out here, the temperature is so high that they're kind of all scrambled up, and down here, the temperature is low enough that this interaction between them is able to bind them together to form a magnetic material. The Curie temperature, by the way, is different for different magnetic materials. So for iron, the Curie temperature is right around, I think, let me look it up. I think I have it here, around 1400 degrees Kelvin. let me see if I have that. 1043 Kelvin is the Curie temperature. So when you have this iron in a smelting oven above 1000 degrees Kelvin, it's non-magnetic precisely because all the atoms are randomly oriented. But as soon as you cool it down below this temperature, then the magnetization gets locked in. And so if it's in the vicinity of the Earth's magnetic field, then the spins which will be oriented, that orientation will be locked in. And even when you take away, if you move it to a different location, you bring it out into space, let's say, away from Earth's magnetic field, that piece of iron will still be magnetized because the magnetic properties will have been locked in. Okay. Lodestones, by the way, are comprised of magnetite, which is a mixture of iron and oxygen, and magnetite is said to be a magnetically soft material. That means it is easily demagnetized. It has a low coercivity. But magnetite also, as it's found in nature, tends to have little inclusions, bits of titanium or aluminum. That makes it a bit more magnetically hard. That is, it makes it a little bit harder to lose its magnetization. That is precisely why Gilbert mentions that lodestones are hard to demagnetize. It's because they're comprised of this combination of iron and other atoms that make them more magnetically hard. Pure iron, on the other hand, is magnetically soft. It's able to be remagnetized quite easily. Permanent magnets, on the other hand, like things you buy from scientific supply stores like neodymium magnets, they're actually comprised of neodymium and iron. So neodymium, a pure neodymium, is a ferromagnetic material, but the Curie temperature is around 19 degrees Kelvin. So at room temperature, it would be way up in that paramagnetic phase, and it would not keep its magnetization. The atoms would all be randomly aligned. But by adding to it iron and boron, other impurities, you can make it magnetically hard and a very strong magnet that retains its magnetization even at room temperature. In fact, I think the neodymium magnets have a Curie temperature, depending on what impurities you put in it, you can have a Curie temperature anywhere between about 300 degrees Celsius and 900 degrees Celsius. Why is neodymium such a strong magnet? It's because neodymium has 4 unpaired electrons, so it gives it a large magnetic dipole moment. Iron ore, like I said, that you find in nature, like lodestones and magnetite, they tend to be not quite as strong magnets. There's also other kinds of permanent magnets, like ceramic or ferrite magnets. This is a very interesting area of study, and I hope I've given you a flavor for the contemporary way of thinking about magnetism and how it relates to the work of William Gilbert, who is really a pioneer in this.